Infinity. Just saying the word, it can feel a little intimidating, right? I mean, you start thinking about endless space or time that just never, ever stops, and your brain kind of starts to hurt. But what if I told you that for mathematicians, infinity isn't this one big, scary monster? What if it's actually more like a whole toolbox, filled with these custom-made inventions they designed to solve really specific problems? All right, let's get into it.
You know, the poet Edgar Allan Poe, he really nailed how most of us feel about it. This idea of something so unbelievably vast that it's literally inconceivable. It's the stuff of awe, of mystery, and yeah, maybe a little bit of existential dread. It belongs in poetry and philosophy.
But then you get this, a totally different take from mathematician Edward Shinerman. Just another day at the office. Wow. I mean, that is a huge shift in perspective, isn't it? We go from the totally inconceivable to just routine.
And that really sets up the big question for us today. How? How in the world do they do that? What's the secret that turns this mind-bending concept into a practical, everyday tool?
Well, here it is, the answer, the key to the whole thing. It turns out mathematicians didn't just discover some single, universal infinity. No, they invented a bunch of different, really useful versions of it. They basically created different flavors of infinity to suit whatever they were working on. And today, we're going to check out 3 of them.
So, our first flavor is probably the one that feels most natural. This is where we treat infinity as a place, like an actual destination you can put on a map. Think of it like the final station at the very, very end of the line. And this picture shows the idea perfectly. You take that number line we all learned about in school, you know, the one that goes on forever, and you just add a point at each end. You give them official names, infinity and negative infinity. And that's pretty much it. You've just created a brand new system called the extended real numbers. Now, the real beauty of this whole setup is how it makes certain kinds of math way simpler. See, if you're already at the final destination, infinity, and you try to add 5, well, where are you going to go? You're already at the end. You're still at infinity. So that gives us this nice, clean, logical rule. Any number plus infinity is just infinity.
But here's the catch, the trade-off. By adding these powerful new numbers, you actually risk breaking some of the old super important rules of arithmetic. For instance, what on earth should infinity minus infinity be? Is it 0? Is it something else? Things get weird fast.
So to stop the entire system from collapsing into contradictions, like proving that 1 equals 2 or something crazy like that, mathematicians make a really clever move. They just declare certain operations off limits. They're left undefined. So asking, what's infinity minus infinity in this system, it's kind of like asking a question that has no answer. It's a move that's just not allowed in the game. And that's on purpose, just to keep all the math consistent.
Okay, so that was infinity as a place. But what if infinity isn't a destination at all? Our second flavor reimagines it as a process, a journey that just keeps going, forever, getting closer and closer to some value, but never quite stopping.
Right. We've all seen this number before. You divide 1 by 3 on a calculator, and there it is. Those little dots at the end, they mean the 3's just go on forever and ever. But think about it. What does an infinitely long number actually mean? How do we even work with something like that?
So, there's this really cool, classic little algebra trick for this. Okay, so follow me here. We'll just call our endlessly repeating decimal x. Now, what happens if we multiply it by 10? Well, that just scoots the decimal point over one spot, right? So now we have 3.333 and so on. Now for the magic part. We take that new number, the 10x, and we subtract our original x from it. And would you look at that? All those endless 3's just vanish. They cancel each other out perfectly. And what are we left with? 9x equals 3. A quick bit of division, and bam, x is exactly 1/3.
But what's really going on under the hood here is this idea called convergence. We're not actually doing an infinite sum. What we're really looking at is a sequence of numbers. First 0.3, then 0.33, then 0.333, and you just keep going. Each number in that sequence gets a little bit closer, a better approximation of 1/3. And this process can get you as close as you could ever possibly need to be.
That makes sense, right? The little bits you keep adding get smaller and smaller, so the total sum should eventually settle down on a number. But what if that intuition is totally wrong? What if you could have a sum where the pieces you're adding keep shrinking towards 0, but the total sum just keeps growing? Forever?
Well, say hello to the harmonic series. This is honestly one of the most famous and surprising things in all of math. You start with 1, you add a half, then a third, then a quarter, then a fifth, and so on. The terms you're adding get ridiculously small. I mean, the millionth term is just 1/1,000,000th. And yet, and this is the wild part, if you just keep going, the total sum will grow without any limit. It goes to infinity. It's a process that never, ever settles down.
Okay, so for our third and final flavor, we're about to take a step into, well, a completely different mathematical reality. We're going to a place where the basic rules of things like addition and multiplication have been totally rewritten. Welcome to the very strange, very cool world of tropical arithmetic.
Now, the rules for this new reality, they might seem bizarre at first, but they're actually super simple. To do a tropical sum, you don't add, you just take the minimum of the two numbers. And for a tropical product, you don't multiply, you just add them together like you normally would. Yeah, the operations are completely redefined.
Let's just see this in action because it's a little weird. In our world, 3 plus 5 is 8, obviously. In the tropical world, 3 tropical plus 5 is 3. Why? Because 3 is the minimum. Okay. In our world, 3 times 5 is 15. In the tropical world, 3 tropical times 5 is 8, because you just add them. It's a complete rewrite of the basics we all learned.
Right now, you've got to be asking, why? Why on earth would anyone invent this? What is the point? Well, the payoff. It's visual. You see, the really cool stuff happens when you ask, what happens to familiar shapes, like lines and curves, when you try to draw them using these new tropical rules?
And here it is. This is the stunning result. On the left, you've got a boring old straight line, but on the right, that's the exact same equation plotted in the tropical world, and it produces this sharp Y shape. Tropical math basically transforms smooth curves into these angular shapes made of straight line pieces. It literally sets everything straight.
So let's just pull all of this together. Let's recap the journey we've been on. We've just looked at 3 completely different ways that mathematicians have managed to tame the infinite.
Right? We saw infinity as a destination, like a final stop on the number line. Then we saw it as a process, that journey of getting closer and closer to a value. And finally, we saw it as the foundation for a whole new set of rules in a kind of parallel mathematical universe.
And all of this brings us to what might be the single most important idea of this whole explainer. Infinity isn't some big, mysterious force out there in the universe just waiting to be discovered like a new planet. It's a concept to be invented. It's a powerful, flexible, human-designed tool that could be shaped and reshaped to solve all kinds of really challenging problems.
And that leaves us with a final, kind of provocative thought. If the whole idea of infinity is a human invention, something designed for a purpose, it really makes you wonder, doesn't it? What are the huge problems of tomorrow going to be, and what new, strange, and powerful kind of infinity will we need to invent to solve them?